level from a exponential smoothing model and looked like, oh wow, why did they kind of look the same? And I wasn't very happy with my answer, so decided to try a different way of explaining it. And so let's think about an exponential smoothing model for some really simple data, some really smooth data. So let's imagine that these are our data. And we want to come up with an exponential smoothing model for this that has level and trend. And what that means is we want to come up with this forecast of the next data point. And that's going to be based on two things we're going to estimate. We're going to estimate basically where we start, which is the level, and we estimate what the trend is. So what does that mean? So if we go back and we look here at our data, so we want to predict the next time point. And we're going to estimate a trend, and but to get the estimate, we have to start somewhere. Right? So we got to start here, and then we're going to go either up or down by a certain amount. So we have to tell it, where do we start? That is what the level is. And the trend is kind of what slope we're going to use. So those are the two things. So I'm getting a lot of noises. Are they not? No, they're not saying anything. Okay. Great. Okay. So if you look at this, hopefully it should be kind of obvious that when you have something that's so smooth here, that the best place to start would just be at the last data point. Because, you know, it's not noisy. It's not like, imagine that this were noisier. And in that case, we were fitting a smooth line through it, would kind of be in the middle. But this is already smooth. So when we fit that smooth line through it, it just is going right through the data. So that's the data. The last data point is the level. I put that in quotes because, like, when you hear level, or when I hear level, I think, oh, here's the level. And in the context of these models, it might be better to think of it as, in these models, a model with a level and a trend, to think about it as the starting place. And then you're going to add on the trend. Okay, so let's look at this with an ETS fit. So the data are that data that I showed. It's just it was just a sine curve. So that's what that is. I'm going to fit a exponential smoothing model, and I have AA, so I've got an additive level and an additive trend. I didn't mention this term here, the damped equals false. The exponential smoothing function, its default when it fits a trend model is that if it's doing a really long forecast, it won't it won't have that trend just going up and up and up and up. It will kind of level off. And that's an ad hoc solution to doing really long forecasts. Well, what people have found is that if you're doing a really long forecast and you just continue this trend like this, like way out here, you're like guaranteed to go way off. And they found that the forecasts generally do better if you kind of sort of level off. It's ad hoc, but that's what they do. And in the ETS, I assumed that that the default would have been damped equals false, that you didn't include that ad hoc feature. But when I was writing up this lab, I was looking at the help file, and actually the default is true. So I don't want that. I don't want that feature. I just wanted to use the smoothed trends. So the average trends, remember I was showing you this idea, either you use the last trend or you use an average of the last few trends. So that's what I want to use. So I'm going to say damped equals false. And what I'm going to pull out of the fit is I'm going to pull out these two, that level term and the trend term. In an ETS fit, that appears in this part called the states. If you look at that, it's two columns. One of them is going to be labeled L, that's that level. The other is labeled B, that's that trend. The first column is the level, and the first data point is an initial condition. I don't want that. And so I fit this ETS model. Like I said, the best level should just be the last data point. And you can see here's the data, and here's that level that it's estimating. Let's see, it's what your intuition tells you it should be. All right, well, let's think about now what the trend ought to be, though. So the trend is upward here, upward here, upward here, kind of flat here, and then downward, downward, downward. And if I told you to make a prediction of what Y is going to be, well, you could look and say, oh, well, the last one was a trend like that, so I should just continue that. Well, if you look at the past trends, did the past trends continue at the same rate for multiple years? No, they didn't. So that actually, you're not using all the information. The information you have is that the trend is changing. And so it would be better to use something that's not quite this steep. Take an average of the more recent, the other trends in the past. So in that case, it should be quite that steep. It ought to be, you know, this is not quite so steep. Let's take an average of these, maybe be a little bit leveled off. So maybe more like that. That's using all this information in the data about the fact that the trend keeps changing. Obviously, if this were going, you know, the trend was always constant, well then, yeah, sure, we use the last one because it's not changing. But we observe it is changing. So the exponential smoothing model is doing that for you. That sort of thought exercise that I just talked through, it's doing that, and it's testing all these different levels of smoothing for the trend. So how much averaging, how far into the past do I average? It's figuring out which one gives you the best forecast, given the data that you have. And so this is the data. And what I'm showing now is the dip dat. So these are the trends. So if we look back here, it's going down, down. So these should all be negative, and there should be about 0, and then these here should be positive. And that's what I see here with the data. Here's 0. These are positive, going up, and these are negative, it's going down. And the exponential smoothing model, its estimated trend, so it's saying this is the best one we should use. It shouldn't be quite so negative, a little bit less negative. And up here near the beginning, says it shouldn't be quite so positive. It should be a little bit less positive. And that's because we're seeing that that's how the trend is changing in the data. And now when we look at the decomposition, this is the observed data. This is that estimated trend. And so you can see these are exactly the same. But that's because of the nature of the data. If I'm going to show you another example, it's not going to look quite like that. This is because the data is very smooth, and so that estimated level that it should be using is just equal to the data. Nothing any more magical than that. And then the estimated slope, well, again, you're like, oh, wow, it looks just like this.
Wait.
Yeah.
I'm confused. Wait, the slope, this thing was like a sine chart. So wouldn't the slope have been 0 in the middle? At like time step 5 or something?
Let's see here. Yeah, but it wasn't. It was about 6. Yeah, it should be 0. Let's see here. Well, that's 4.
So it's the most positive around there.
I think it's offset here. Offset. 1, 2, 2, 3, 4, 5.
Oh, maybe I'm just tripping the scale.
There's an offset here because it's got these extra 2 starting points, so it actually starts kind of.
So it should be shifted
here.
back too.
Yeah, so it's shifted.
Okay. Yeah, it looks like your zeros are on 8.5, 9.
Yeah, the 0 is about. Yeah, that is kind of strange. Look, this one.
Yeah, so
at about 8.
yeah, what is BT?
That's that estimated trend. Okay, so it's taking the average. So we expect that that estimated trend is not going to be 0 here because it's this, and then it's got some of that, and it's got some of that. So here, it's still going to be negative.
Right.
It's not going to hit 0 until about here.
Right. Right.
So we expect that to be shifted.
Still expecting it to be going up.
Right. At that level, and the slope are looking. So that's why they're looking the same, because it's going up, then it's going down. But let's look at another example. Look at some longer data. I think this is kind of interesting. So now I've just lengthened that sine curve out, and it's still really smooth. So it should be a surprise that that level, sort of where we start the forecast, is still just the actual data. Okay, so basically it's fitting a smooth curve through this, and it should surprise you that a smooth curve fit through smooth data just looks like the data. What's interesting though is that the slope estimate is not varying all that much. It's going from about -3 up to, what, -1, which is kind of different than, no, maybe it's not that different. What's interesting to me is that it's going, it's staying negative, and I'm not entirely sure why that is. I had a good explanation, But as I'm standing up here, I realize this is 0.3. I was thinking, and when I first looked at this, I thought it was 0.3 to 0.1, and then I had a really nice explanation why we shouldn't include the trend. But it's actually 0.3. So I don't know. I have to dig into that more. Okay. But let's look at another example where we have noisy data. Okay, so let's imagine that our data look like that. And now that smooth level, put a smooth line through this. It's this happens to be what was output by an exponential smoothing model fit to these data. And now you think, okay, well, what trend should I be using? Well, I should be using these trends, really. I should be using the trends from the smooth estimate here. And that's what it's doing. It's using that, if you looked at the diff of this level, the diff of that level is what is being used for the trend estimate. But when we plot it with the diff dat, you can see that it's kind of doing what you would expect, which is kind of like a smooth line through those differences. Okay.
Wait, I just have one question.
Yes, please.
So this is estimating the trend through the residuals of the data against that level, or no?
So what I'm plotting, no, I don't think so. I'm just plotting the diff dat, which is like the changes in the data, and illustrating that the trend estimate that is coming out of the exponential smoothing is, you can kind of think of it like a smooth version of that diff dat.
Okay, that makes sense.
I'm saying kind of, because actually what it's doing is using the diff of this line here.
Okay.
So it's using those trends, smoothing that.
Is it actually doing that, or is that just what it comes out to be when you average the slope between like two different points? Like, is that the same thing?
It's actually using the diff of the L, yeah. Yeah, if you go, so I put this on the reading, you can read all about these exponential smoothing models. I'm here in this book, Hyndman and Athanasopoulos. And so there's a chapter on exponential smoothing. And let's see, where is it? Trend methods. CPS are written. Yeah. So the way you actually fit these models, I mentioned on Tuesday, is you convert them to a type of state space model. And it looks like this, plus there's some error terms here that are not being shown. But this level is a function of the diff in that level process, and then it's autoregressive, so it also depends on itself. And then the level is a function of its past value and the past value of the trends.
Yeah, actually, I think my thinking was kind of backwards. The difference is what I was trying to describe. It's the same thing. Yeah.
Okay.
Okay.
Okay, so now we're going to jump into covariate models, models with covariates. Where are we? Okay, here we go. Second one. Okay, good. Okay, so covariates. Why might we include covariates in a model? Well, some of them are obvious. Often we're interested in knowing the cause of variation that we see in our data. So this is one example we like to show. This is the variation in purchases of wings, wing sales, and you can see they peak. This has got to be on the weekends, and then we saw a really big peak right here, 2013, which is Super Bowl. Kind of related to that is that we can use the covariates to explain what happened. And if we can do that, maybe we can use them to help forecast something. So an example that we work on at Northwest Fisheries Science Center is forecasting salmon returns. And one example of some work we've done is using a variety of different covariates. So chlorophyll A anomalies, southern copepod biomass, northern copepod biomass, a whole series of things, temperature, using a suite of covariates that are related to salmon biology in the ocean. Yeah, this is all ocean survival stuff. And then using that to come up with these forecasts for future years. In this case, the green is really good. So this is PDO, say. So PDO is really good in this year, in these 2 years, and not so good there. Not that great in 2014. So that's one reason we often use covariates. Oh, wow, I left something off. Oh, okay. But for time series models, another really important reason we include covariates is to explain autocorrelation and our errors. So there are two types of errors you're going to have in your models. We've been working with state space models. We've kind of been working also on non-state space models. So when we're doing ARIMA models, those are non-state space. But the last 3 weeks, we've been working with state space models. And in those models, we have our process errors, and then we have our observation errors. And we can have autocorrelation in either of those. And autocorrelation in your observation errors can be really problematic. So let's use an example, like if you're doing a marine mammal survey and you are surveying a coastline, you're doing it about the same time of day, then you would expect things like tide is going to create this autocorrelation in your surveys, because tide level is related to sightability of, I was thinking of seals, not like dolphins or something. So if you're looking at like something that's hauling out, say seals or sea lions, your tide would affect your sightability. And so you could definitely get some autocorrelation in your observation errors. So how do you deal with that? You can model autocorrelated errors, and I'm going to show an example of how you might do that with a linear regression. But with a state space model, what you would do is you would have this separate autoregressive model for your errors. And then that, instead of having your, so you've got like your observations equal your state, and then you have your errors. And what we've been assuming is that those errors are not temporally correlated. What you could have instead is that you have your observations equals your unobserved state, which is let's say like its population size, plus an unobserved second state, which is your errors. And you model your errors up in your X equation as this autocorrelated thing. Okay, you could do something like that. You're starting to get into some hairy numerics, so you're in danger of creating these likelihood surfaces that they start getting flat, start getting ridges in them. It just becomes hard, no matter what technique you use to fit them. If your likelihood surface it starts getting flat or ridges, it's going to be difficult. So alternate approach is to include a covariate that you believe or have reason to believe or you can show explains that autocorrelation. That autocorrelation could be temporal. It could also be autocorrelation among the sites that you're looking at or the species. So you're doing a multivariate response. And if you have autocorrelated errors among those different responses, that's a problem too. So when might that come up? You're doing trawl surveys, and your multivariate response is 5 different species that you're catching. So they're all being caught in the same trawl. If they all have kind of similar sort of life history, might not be unreasonable to think that whatever errors you have are correlated across all these species because you caught them in the same trawl. So something like that. So, but if you had a covariate that might explain those errors, you could include that in your model and get rid of the autocorrelation across the species. Okay, so that's another reason we include covariates, is to deal with spatial and temporal autocorrelation in our errors, either observation errors or our process errors. Okay, so I'm going to talk a bit about multivariate autoregressive state space models with covariates, and you're going to go through a lab and do some homework on this case. But before I jump into that, I'm going to talk a bit about other approaches. And in fact, these other approaches you are likely to run into more often. These are much more complex approaches, and these approaches, linear regressions, multivariate regressions, have been around for years and years, whereas the state space models have been around less, and not as many years. Okay, so let's think about a multivariate regression. So can you use a linear regression? So just like an LM, function, can you use that with time series data? And so that's your response data is a time series, and you predict, or your predictor variable is a time series. Yes, you can, but you need to be careful. You should read the chapter in the forecasting book by Hyndman, and I'm not going to say his last name this time. Read that. It's going to go all through the various diagnostics that you do when you're doing a linear regression on time series data. The basics, however, are that you need to check that your residuals are temporally uncorrelated. And you do that visually, and there's a number of different tests, standard tests for residuals of linear models. Use those tests. This chapter will describe those tests. You also want to look at your residuals against your predictor variables. You want to make sure that there's not any patterns there. So when you do your pairs plots, everything looks nice and cloud-like. Okay, and then you need to be careful about spurious correlation, and how this often arises when we're doing linear regressions on time series data is if our response variable has some like linear trend, so some temporal trend. It doesn't have to be linear, it's just some temporal trend, and our predictor variable happens to have the same trend. And it's possible that maybe the predictor variable is the trend in that is causing that trend in your response variable. But often, like, just think about like, so economic examples. They're looking at some of the response variables, something like GDP. It goes up for many different reasons, and they're trying to correlate it with something else, like, say population size. Well, that also is going up for other reasons, but they're trying to correlate these two. And so if you just plug them both into the model without having another way to explain that trend in the response variable, you're going to come to the conclusion, wow, there's very strong correlation, and I can explain GDP with population. So what one does is includes time as a covariate. And it could either be linear or it could be some polynomial. So you're allowing for another way to explain the time trend in the data, and you're using your covariate to explain any variation around that trend. The forecast package has a function called TSLM, which makes it really easy to include these time trends. So they include its time and then also a seasonal one. So just look under, if you look at this chapter, they talk about this TSLM function. The TSLM function is nothing really all that special. It's like a wrapper for the LM function. It just makes it easy to include that time trend. There's another type of spurious autocorrelation you can run into, and that can happen if both your data and your covariate are autocorrelated. And we run into this when we're looking at fisheries data, because oftentimes our response variable is something that is biologically autocorrelated. So if you're measuring something that is population size related, yeah, it's autocorrelated. The population size tomorrow is related to population size yesterday. And it's going to be really obvious. So that's an example. There are many other examples, gene frequency, movement. Many of the things we look at are just fundamentally autocorrelated. And oftentimes we're trying to explain this autocorrelated response variable with a covariate, and this is just like a sort of cartoon of the covariate. And the covariate is one value here, and then it's slowly changing to another value. And if your covariate is highly autocorrelated, then you can get this spurious autocorrelation. So there's a couple things that can happen. One, it could just be spurious. And so you're saying, yes, they're correlated, even though they're possibly not all that correlated. And the other thing that can happen is that you are using too big of a sample size. So if you kind of think about this, think, well, okay, I got 20 data points here. Should I really be using a N of 20 when I am computing the standard errors on the estimated effect size of this covariate on this, when this is highly autocorrelated? And no, probably not. Another way to think about that would be like if you're doing a, say you were doing a spatial survey, which is very related to temporal surveys. So you're looking in space, and I was sampling here, and this area has one temperature, and this area has another temperature, and I sample a whole bunch of times here, and then I sample a whole bunch of times there. It's sort of the same issue. No, I don't have 20 samples. I really have more like 2 samples. We're running up against something like that here. I don't know a simple solution for this where you're doing a linear regression. What we're going to move into next is looking at autocorrelated models, where you include in the model you try to predict this based on this plus this. And that class of model doesn't run into that problem because it explicitly is including this. You might be able to do that in a linear regression. You include the past values in there, possibly. I haven't done it, but I was searching to see how people dealt with that problem, and I didn't find anything in particular. Okay, so that's vanilla linear regression. If you take home anything there is look at your residuals. If they've got autocorrelation, stop. You got to deal with that autocorrelation. Don't just plow ahead with highly autocorrelated residuals. Okay, so you've got autocorrelated residuals. What do you do? So one approach is a common approach is to model those errors as a autocorrelated process. So here is an example. This is a linear regression of Y against a covariate D. These are my errors. And now instead of thinking of these as independent, instead I'm going to model these as some autocorrelated process. In this case, I've just happened to write down an AR2. We could have a, AR1 with an MA2, whatever. Whatever combination of ARMA models we've seen, we can have the same for our errors. The ARIMA and ARMA models allow you to fit this class model. And the way you do that is you include this argument called xreg. So in ARIMA, it would look like this. This would be your data. Those are your covariates. You can include multiple covariates. And then you specify the order of the model you want to fit. Or you could use auto ARIMA, and it's going to search over different AR and MA orders for you.
Quick question.
Yep.
If you're selecting covariates with that, like you don't know.
You're not selecting covariates. No,
So,
you are specifying covariates.
okay, so yeah. So you would do the covariate selection process before.
Correct. Yes.
Hold on. You're saying you're doing your covariate selection before you're putting it into ARIMA?
Correct. This will not do any selection for you. It is fitting this model with, however many covariates you have.
Sure.
They're all there.
Oh, no, I get that, but why wouldn't you do your model selection using this? Using like a stepwise AIC?
I think you would, but you can't use auto ARIMA. Auto ARIMA doesn't have functionality for
Yeah, I would imagine you do auto remount like full model or something like that.
Right, but you do auto remount like different covariate sets and compare those.
Yeah.
Sure.
When you select your covariates first before specifying the residuals.
Well, you,
But your residuals
you
are
want
all
to
correlated,
compare
so how do you interpret
I think you want,
that?
Yeah, I think you'd have to you got to do both of them, right? Because for some models, like if you have the covariates that explain all the autocorrelation,
right.
then your errors going to be autocorrelated. Yeah, but then how do you? I'm not sure.
I don't think you can
Yeah.
trust. If you know your errors are autocorrelated, how can you trust that those AICs? Because you're overfitting. I mean, you're not overfitting it, but I mean, you're basically getting a misleading fit.
Well, well, it depends what the AIC. It has some process, some statistical model that's being used to compute the likelihood. What statistical model was that? So if it's a model that has autocorrelated errors, then you're okay. You have the autocorrelated errors. But if you're using the say LM, which is assuming uncorrelated errors, and you're using step AIC or something with that, then you have problems, because in that case the likelihood is being computed assuming with a statistical model with uncorrelated errors. But you could do something where you're fitting this, and then you're changing the covariates that you're including. I think that should work.
Is there a penalty on, is there a parameter for autocorrelation in the error? Yeah, there is. There's like the fee for like how autocorrelated they are or whatever.
Yes, so that's what ARIMA is, and well, that's what this is doing. So this order, it's not for this, it's for the residuals. Yeah.
So like I was just thinking for AIC, if you're comparing a model that had a covariate that explained the errors versus some autocorrelation term, it would just, you'd still be getting a penalty of 2 in AIC for each one of, for the autocorrelation term or the covariate term. So whichever one explains more would be the.
Right. You're still estimating a term.
Yeah.
Right. Yeah. So here's an example from the Hyndman book, and this is a case of explaining quarterly changes in U.S. consumption based on personal income. Those are the data. And if we just did a linear regression, so Y is consumption, our covariate is income. We did a linear regression here. Then we use check residuals. Remember, this is in the forecast package. It's going to plot our residuals here and show us the ACF. And so we immediately see we have problems. And those look a bit too peaky there. That's our normal curve. Let's try AR1 errors. Kind of filled our residuals curve out just a little bit, but we still have problems here. We can let AutoArima find it, and it chopped off a bit, but it did better. Gotten rid of that short-term autocorrelation there. the model that's chosen by Autocorrelated is the AR1 MA2. And again, that's for the residuals. All right, so collinearity. That's a really big issue. And if you're thinking about doing stepwise variable selection, you should do a search on the issue. And you can read the chapter I wrote on doing that in the context of catch forecasting. Many statisticians hear stepwise variable selection and they go, it has a really bad rap as being synonymous with data mining. And in the context of developing forecasting models, what happens is that you overfit the data and you find patterns that are spurious, and then you use spurious patterns to make forecasts, which not surprisingly are bad forecasts. See if this comes up. Yeah, okay. So I wrote up this chapter for fisheries catch forecasting. So in catch forecasting, so they're just using a catch time series and they're trying to use some covariates to explain that catch variability. There's a little cottage industry in doing this. People do this a lot. And they use stepwise variable selection widely. So even though, so with a caveat that statistician would be like that, I wrote up information on how to do this, how to do stepwise variable selection in R and the various approaches that you have. And R is really good for doing it. There's a lot of different approaches that you can use and a lot of different ways you can evaluate how your covariate selection is working. You can test different ways to do the variable selection. So you can select based on AIC, you can select based on BIC, you can select based on other metrics, you can compare what models are selected. It's, yeah. Let's see, and there's this. Yeah, oh, okay. I should back up a little bit and tell you about the problem that happens with collinearity. So this is an example where what I'm trying to do is forecast, I'm trying to predict the anchovy catch based on a series of covariates, some environmental covariates, air, sea surface temperature, wind direction, and also some fisheries covariates. So this is horsepower, total number of boats, total number of fishers, year, and then also another species. So this is this kind of pattern where you have one covariate coming out really positive and another one coming out very negative is the classic collinearity problem. So it turns out if you did a pairs plot, you would see that year and top are collinear. There it is. Yeah. Year, top, horsepower, also same thing. So year and horsepower. So as years go on, this is for the Greek fishing industry. The fishing industry is growing. More and more horsepower. So it shouldn't surprise you. There's that linearity there. And then the classic thing that happens when you have two collinear or multiple collinear variables in your model is one gets really positive and one gets really Okay, so if you're interested in that, you can read all about that, but I want to briefly tell you one approach that people use instead of doing stepwise linear regression. Instead, they do penalized regression. So in a penalized regression, you include all the variables. You don't try to pick the one, you include all of them, and then you you sort of like those variables, the estimated effect sizes that get really positive or really negative, you kind of pull them in. You don't allow those really extreme values. You pull them all in. So here's an example. So this is ordinary least squares. So this is just what you'd get out of an LM. And this is a ridge regression. And you can see how they're all getting pulled in. There's a different type that's called lasso regression. A lasso regression will set some of them to 0. So if they get really small, you'll go ahead and set them to 0. So you notice in the ridge regression, none of them are set to 0. In lasso, we're going to have some of them disappear. So has a little bit of the features of stepwise variable selection. So stepwise variable selection, you get rid of variables. Ridge selection, you don't. So lasso, we have some of the features of both. So here's black is the lasso, and then the orange is the ridge. And you can see in the lasso, we've gotten rid of those two up there that were highly collinear. And then there's elastic net, which is a little bit of both.
Good name.
Yeah. The nice thing is that it's really easy to do all these types of penalized regressions in R. And then once you can fit all those different ones, then it's easy to do cross-validation to look at the performance of the different models. Okay, so let's go back to, that's not where I want to be. That's not where I want to be either. Okay, so now let's switch gears and we're going to talk about including covariates in MARSS models, so these multivariate autoregressive state space models. This is related to what's called a ARMA-X model. The ARMA-X would be if we didn't have the Y here, we just had the X up here. So this is a ARMA. See, it's ARMA AR1, and then our covariate appears like this. When we talk about MARSS models, we have also this observation process, and we can also include our covariates in the observation process. So what is different now is that I'm explicitly explaining the process errors or the observation errors with my covariate. And my process model includes my autoregression in the process. So when I did that ARIMA and I had the XReg, there wasn't auto regression in the process. It wasn't like YT is some function of YT minus 1. No, it was YT is a function of all my variables, and then my residuals are autocorrelated. So this is different. We've got this autocorrelated process here, and then you can think of this part as being those not really the residuals, but the process errors. And those process errors are a function of my covariate. This makes it, well, one thing this does is it makes it much easier to make the biological connection. So if you are thinking about that, let's say your X is population size is at time t, some function of population size is time t minus 1, and then how much it changes year to year is some function of the covariate. So if the sea surface temperature is warm, it's a really good year and the population grows more. So it has this really natural biological explanation. And so often, like when we're up there at the whiteboard and we're all thinking about, okay, how do we structure this model? How do those covariates come into play? We're not writing it down necessarily as an equation, but our words are acting like this. Because we're thinking about, okay, how far do I move? Or how much do I grow? Or how much does it change? It's being driven by some covariate. Okay, so why include covariates in this class of model? As I mentioned in the beginning, one thing is you're trying to explain those process errors, and you're using the covariates. Another reason is you are explaining your observation errors with your covariates. And you can do both at the same time. In the lab, you're going to do both at the same time. Types of covariates, we can have continuous, things like, it would be like temperature, discrete. We're going to be using the continuous quite a bit. Categorical, though, is another common type of covariate. And so that could be like before, after. Would be common. Another typical type of categorical could be site or month if we're doing a seasonal model. Right, so as I said, we can either have these covariates appear in the process model or in the observation. When written like this, these W and the V are assumed to be independent and identical. Not identical, but independent. So they are multivariate normal. So they're not temporally correlated. And whatever temporal correlation that's happening in the residuals, I'm explaining that with my covariates. But I can still have patterns in these leftover areas. So these are now the residuals here. Residuals. I could still have some pattern across my either response variables or my underlying states. So I could model that, let's say I have Y is 3 different locations. So any temporal correlation is being accounted for with these covariates, but I can still say that my sites, 3 different sites, are correlated. And I would do that by having a non-diagonal R matrix. So I've got covariance terms in that. All right, so let's look at these C and the C matrix and this little c. The little c are the covariates, and it's going to be a column vector. There are k covariates in this example, and this is the covariance observed at time t. We can't have any missing covariates here. I'm going to talk towards the end about how to deal with missing covariates. So I've got all my covariates here. Let's say I have k of them here. This matrix here, the C matrix, is the effect of the covariate on the state. So this is going to have k columns, because this has k rows, and it's going to have one row for each state. Same thing for the D matrix and the D. The little d are the covariates. So these are the covariates that are affecting the observations. I have k here, but it doesn't have to be the same that are in the process model. But there's one column, all the different covariates, and then we're going to have the same number of columns here, and then in rows, one row for each observation. What that allows is us to specify what the relationship between the covariates and the states or the observation is. So let's see an example. We have our C. We're going to model something where precipitation and nitrogen we think are affecting our state. So they're affecting, let's see, precipitation and nitrogen. So we've got some phytoplankton. Okay, so it's affecting our density of phytoplankton, and we have 3 different phytoplankton, say, populations that we're monitoring, and we could set up our C matrix like this, and what we would be saying is that in each of these 3 populations, precipitation and nitrogen have the same effect. The size of that effect is the same. Or we might want to test a different model, which was that the effect of precipitation and nitrogen are population dependent. So that might be just a hypothesis that we have, is which one is it? We could test that by seeing, looking at the data support for these 2 models. We could set it up that precipitation effect is population dependent, but the nitrogen effect is not population dependent. So the nitrogen could look like this, while the precipitation effect looks like that. So we can specify all those different constraints and then test support for different structures. Okay, so this is what you're going to be doing in the lab. So in the lab, you're going to be working with a long-term data set on zooplankton in Lake Washington and a bunch of covariates, and you'll be testing how the covariates impact the different species, whether it has similar effects on the species or different effects on the species, and you'll be testing whether the covariates should be coming in on the process side or on the observation side. So you can see, so like imagine like you're monitoring something, and you see that every time the nitrogen goes up, you start collecting more of a certain species. Well, is that because nitrogen affects the growth rate, so there's really more of them there? Or is it because they're all attracted to the nitrogen and they come up to the surface and you're able to catch them? Right, so there's not more of them, you just see them. They're easier to catch. And So you're going to be testing those ideas. Are the covariates coming in on the observation side, or are they coming in on the process side? Yep.
If you have a whole bunch of covariates, how would you decide which ones to include in your model? Because this like assumes you know it's going to be like one or two, right? And then you can fill in the structure.
Yeah. So then you're getting into that question of variable selection, and the way that I have done it is developing those covariates, developing a set of non-collinear covariates. So doing a lot of looking at the covariates. I want to make sure they're not collinear, and then selecting the covariates based on discussions with the biologist. And if they are collinear and I want to, or the biologists say, yeah, we definitely need to include both of these, then coming up with a variable that either includes both of them, or I need to include one and then include like so you have two collinear covariates. You include one covariate, and then you have this other transform covariate, which is everything left over that can't be explained by covariate 1. So it's the same idea if you were to do a polynomial regression. Say you wanted to do a polynomial regression with time. And so you had time, which was year in your model, and then you had year squared. So you wouldn't want to include both of those in your model because it should be obvious that year and year squared are collinear. So instead what you do is you include year, and then the second covariate is everything in year squared that is not explained by year. So you create these two orthogonal things. The second thing doesn't really look like, so the second covariate, so your year squared doesn't really look like year squared, but actually it has the same information as year and year squared.
But interpretation of that second covariate would get a little bit, like it wouldn't be a straight like interpretation of it.
Correct, yeah, right. Okay, any other questions about those covariates? I'm going to jump now into seasonality. Okay. So, season. So, season can be included in a model in a few different ways. Let's see, do I have, okay. So one way is that you include season as a factor. A factor would be like in a linear regression, sort of, red, blue, white, male, female, those are factors. And you can include season also as a factor. And when you do that, you create a covariate that is either a 1 or a 0. So this okay. So this is time 1. At time 1, I would have Okay, let's step back here. Let's look at this C matrix. By the way, this is the way that in the internal workings of the LN function, it's doing this for you. When you're working with the MARSS models, you have to set this up yourself. And it's a little tedious, but it's actually not that hard once you get the hang of it. So you have your C matrix, and this is your effects. So if we have winter, spring, summer, and autumn, we have one for each column. And this would be the winter effect for, we're saying that it's the same for all populations. There are 3 populations, population 1. So we've got each row here is for an X for a population site. So that's our winter effect. This would be our spring effect. This is our summer effect, our autumn effect. And in T1, if we're in winter, then we have a 1 in the top row. And now you can see when we now multiply this by this, we're going to have all the other seasons zero out, and then we're just going to have the winter effect appear. In the next time period, we're now in spring, and then our covariate column vector looks like this. We've got a 1 here in the second row, and now you can see, multiply that C2 comes in. So that's how models that have factors do it. They just have these, a covariate that is zeros and a 1 in the right row. So if you go through time, you have winter, spring, summer, autumn, and now when we start over again, time period 5, we're back to winter, and so we have a 1 back up here again. So we keep having these blocks of kind of diagonals. So when you're working with the MARSS package, you set up this matrix of your covariate for your factors. Okay, so that might seem okay if you only had 4 periods, winter, spring, autumn, fall, that's 4. But what if you had 12 months? Yikes, now we've got 12 parameters. So that could quickly overwhelm the number of parameters that you can really estimate given your data. So another, 2 other approaches are common. One is a polynomial, and the other one is using combinations of sines and cosines. So if you're using a polynomial, then you're going to have your covariate look like this, 1, and then right. So we've got that's not really what I want. So you have, this is month 1, month 2, month 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then we start over again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And so it's in these groups of 12 columns. So month 1, and then we have a month squared. Wait, this is not what I want. Okay, back up. All right. Okay. So in a cubic, when we include, in this case, we're going to do the month. So instead of having a factor for each month, we're going to include month as a cubic. So we're going to have 3 covariates. It's going to be month, month squared, and month cubed. So this is our covariate matrix. We have one row for each covariate, so we're going to have 3 covariates, and then we're going to have one column for each time period. So this time period is month 1. So month squared, month cubed. Month 2, there, month 3, month squared, month cubed, and this is going to go up until we get to time point 12. That's month 12. It'll look like this. And now in the next one, time point 13, we're back to month 1, and it goes back to here. We just keep stepping through. Obviously, if time point 1 wasn't month 1, then it wouldn't start with 1. It would start with whatever month it was. So the nice thing there is now instead of 12 parameters we're estimating, we only estimate 3. So that's nice. We can get it even lower if we use combinations of sines and cosines. So, so you're comparing like the factor versus the polynomial versus the Fourier series. So with the factor, you could have any shape of the month effect, right? You put no constraints whatsoever on that. But now with that polynomial, depending on the order of the polynomial, we've restricted things. So if we had a second order polynomial, right, we could have things that look like that. We could have things that look like that. Things that look like that. But we can't have that. Third order, or at least now we can do some other things, but still we're kind of limited. It's got to be fairly smooth. With the Fourier series, now it has to be, it also has to be smooth. So we're limiting it, but this can work is if you know that your seasonal pattern ought to look kind of concave-ish or like that. And what you do here is your 2 covariates are going to be a sine and a cosine, and you'll have time here. And then you have the period that you want. So in this case, the period would be 12 if we had months, but if it was quarter, it would be 4, or if it was 24 hours a day, etc. So now we just have 2 covariates, and we're estimating that many fewer parameters. Okay, 56. Let's take a break, and I'll talk a little bit about missing covariates, and then you'll start playing with that in the lab. Okay, so let's take 10 minutes. Yeah.
So the data that I'm looking at for my project, remember those fish catches? They look to me like a mixture model, like finite, like
This conference will now be recorded.